Hello all. So this is going to be a little bit of a different video than the ones I've done previously, but I wanted to do some more teaching, right? Because it's something I really enjoyed when I was in school. So I thought I'd go over some of the things that I've learned as a chemical engineering graduate from Georgia Tech and hopefully help you succeed in chemical engineering as well. So again, my name is Anu. I am a chemical engineering graduate from Georgia Tech. I graduated with a 4.0 GPA, high marks, and I went on to work for Dow Chemical Company, so one of the largest chemical companies in the world. I'm no longer with them. I left the company back in January, but this is my way of giving back and kind of teaching a little bit of the skills that I've learned. Now, the fundamental thing to understand in chemical engineering is mass and energy balances. This is the foundation for everything that you do. Essentially, every class that you learn after mass and energy balances is just to refine your understanding of mass and energy balances. So you can get a little bit more refined and you're making less guesses and less estimations and less assumptions. That's all you're really doing once you go on to further and further classes. Alrighty, so with that, let's get straight into it. Essentially, we're going to start with just mass balances and we're going to talk about very simply a black box, meaning we have some sort of box that represents our unit operation. Now, if you're not at the point where you know what a unit operation is, in chemical engineering, that means a reactor, a distillation column, a flash column, anything where something is happening to the mass that's going on. You might have some streams coming in, you might have some streams coming out, and then you have things going on inside of the unit operation. So the big equation that we want to know when we're talking about mass and energy balances is the accumulation of mass inside this box is equal to what's coming in minus what's coming out plus what's being generated minus what's being consumed. Now this is the equation that you use pretty much all the time. Not pretty much. You will use this all of the time when you have a mass balance problem. And this formula is the same for energy balance as well, but I'm going to focus specifically on mass balances here. Right. So just a couple of things that you'll do in your first mass energy balance class is you'll be able to simplify this a lot, right? So a lot of times you'll be at steady state. So what does steady state mean? It means we the state is steady, it's not changing, which means that there's no change in the amount of mass that's inside the reactor. It's at a set point. So this accumulation term will go to zero. If we're doing a total mass balance and we're not working with like nuclear chemistry, well, you can't generate or consume mass. That's consumption or conservation of mass. That's the term that we use. So then we can get rid of the generation and consumption terms. Right. So let's give a practical example here. So suppose I have a reactor where we have two species, A and B, with the reaction A goes to B. You feed some A in, and then out comes whatever's left over of A that wasn't reacted, and then of course your product B, right? So this is just one unit operation is the reactor, right? And so we want to do the mass balances for this problem, right? And so let's just define our total mass as the amount of A plus the amount of B in the reactor, and then we can set up our terms. So we have accumulation equals in minus out plus generation minus consumption, as we stated before. So total mass balance, so the accumulation term or the change in mass over the change in time, is equal to the mass in minus the mass out. And since it's the total mass and we're not working with nuclear chemistry, there's no generation or consumption, so we are done. This is it. dmdt equals mass in minus mass out. Now we can break this down further because we actually have the amounts here. So mass in is equal to A in minus the out terms, A out and B out. Okay, let's do the same thing for A. So now I can say dA dt is equal to A in minus A out. There is no generation of A. We're going to assume the reaction is irreversible. It only goes to make B. But there is a consumption term. So minus, right now I'm going to write it as A consumption. And likewise B dB dt is equal to B in, which is 0. So we can get rid of that actually. So minus B out plus the generation term, which is B consumption, or sorry, B generation. And we know that A consumption equals B generation. And this is it. This is all mass balances really are, right? And when you solve these, it's just a matter of like knowing what constraints that you need to put in, right? So for example, if we're at steady state, then all of these differential terms go to 0, and now we're solving an algebraic equation rather than a differential equation, which should be nice. This is why a lot of the interlevel problems that you solve in your first mass and energy balance class will be at steady state, right? We're just starting with algebra. And hopefully you can see that as you get more and more advanced in chemical engineering, you start to see where we can actually introduce more of that complexity, right? When you take kinetics and reactor engineering, then you get really familiar with what to do with the consumption and generation terms. Okay, now you have extra details. Okay, it's a first order reaction, and with the rate constant, you don't need to worry about what this is if this is unfamiliar. Let's say you have a rate constant and it's first order reaction. Now you actually can replace these terms that you didn't know with the appropriate rate equation, right? If you have separation columns, right, there's different equations that you also incorporate. As you get more and more familiar with this, you will start seeing how extra terms will come in and you'll start making less assumptions. Obviously, the most simplest problem is you have a steady state problem and all the terms are pretty much given to you, or there's nothing interesting happening. Like you don't really have a reaction. It's just a kind of simple, I'm splitting two things, right? But as you get more complicated, you can actually make less assumptions. Okay, it's gas phase, but it's also not ideal, so I have to make some correlations there. I have a reactor that's having some interesting kinetics, or there's a catalyst. Okay, now that's some interesting kinetics. I also care about the concentration of catalyst and the catalyst flows in and out of the reactor. So all of these things can be things that you can add and actually complicates the mass balance. But this is the most important part, being able to set this up. Energy balance is the same thing. Accumulation equals in minus out, plus generation minus consumption. I'll create a separate video for energy balances. All you need to know is it's the same thing, right? Change in energy or the change in time equals in minus out plus generation minus consumption. If you're not working with nuclear chemistry, then the total energy of the system you can't change. There's no generation or consumption of energy. So it's just in minus out. So I don't want to leave you without actually working through an example of a mass balance problem. So here's one. This is one that's commonly taught in a differential equations class, where you set up the mass balance, but we're going to actually solve it for steady state here. So basically we have a dilution setup. So we have salty water, that's this stuff right here, that's coming in, and then we're feeding it with equivalent amount of water that is not salty, right? So just clean distilled water. So we're diluting it, mixing it around. We're going to assume that this is pretty well mixed, and then we send it out. So the question is, what is the steady state concentration of salt and water inside the tank, right? So just so that we have defined everything, S is kilograms of salt in the tank, or the solute, and W is the kilograms of water, the solvent, in the tank. Okay? So we can set up our mass balances here. We only really need to set it up for two of the systems, right? So we can do it for the salt and we can do it for the water. So again, accumulation equals in minus out plus generation minus consumption. And there's no reaction happening, so none of these should have generation and consumption terms. So accumulation equals in minus out. Pretty straightforward. So we'll do water balance first, because that's easy. Change in the water concentration over time is equal to whatever water is coming in. So we have a total of 200 kilograms of water per hour coming in, minus whatever's coming out, which we don't know yet. So we'll just define this as x kg water per hour. So minus x kg water per hour. We need to solve for x. The next one is the salt one. This one is, remember that the units for this one is kilograms salt per hour. And so what is the salt coming in? Well, we have kilograms salt per kilograms water. So 0.05 kg salt, kg water. And then we also have a flow rate here. So this is 100 kgs of water per hour. So when you do the units cancel here, and then you are just left with the correct units, kilograms salt per hour. Then we think about what's coming out, right? Now, what's the concentration coming out? Well, since we assumed it's well mixed, basically the concentration coming out is what's going to be the concentration in the tank. So we have S kg salt per W kg W. Okay, so that means outwards is going to be S over W kg salt per kg water times X kg water per hour. So again, these terms will cancel. Now we said it's steady state, so we'll set these equal to 0. And now it's just a matter of solving for each of the variables now that we have our equations. So this one, we see that x equals 200. Hopefully that's clear. Kilograms. Oh, x is just equal to, yeah, kilograms of water per hour. And then this one, we have 0 is equal to 5 minus S over W times 200 minus 200 times S over W. So since the amount of water in the tank doesn't change, I should have given you that information earlier. We'll say that this one has, to start, 100 kgs of water. So the amount of water is not changing in the tank. So this becomes 5 minus 200s over 100, or 5 minus 2s, which means that the final solvent, or the final solute concentration, or the final salt concentration, will be 2.5 kilograms. All right, that's it for this video and this example. I will see you tomorrow in the next one.